Hello, my name is Haru, and today I am presenting our work on learning model predictive control with aerodynamics regression for autonomous racing, which is a model-based robot learning approach for learning the dynamics of a robot and optimal control policy simultaneously. The learning problem is formulated in an optimal control paradigm, enabling deployment on extremely safety-critical and agile systems, such as a race car. This video plays the vehicle of Team AI Racing Tech driving in the ED Autonomous Challenge. This fully autonomous Indy car is capable of reaching 320 km an hour, and the MPC driving the vehicle is capable of achieving 90-95% of professional race car driver performance. It represents one of the state-of-the-arts in autonomous racing. Our major issue blocking the achievement of full potential race car driver performance is the lack of dynamics model data at the limit of handling of the vehicle, and this facilitates learning-based methods to fill the gap. The learning MPC pipeline is designed for such a task. We initialize the controller with some recorded state and action of non-expert or near-expert policy. Then, in every iteration, learning MPC builds a bigger dataset of some new state and action pairs, query from the dataset to learn a better policy, which we will discuss next, and repeat the process until the policy converges to an optimal point. The dataset in learning MPC is called the sample safe set, or SS. It is interesting in real-world robot learning because it offers invariance and reachability. If the environment has not changed, then we know that as long as the robot can reach a state in the sampled safe set, it is guaranteed to complete the task, because the previous iteration of data have proven that this trajectory will lead to the final state. This property motivates us to impose a safe set constraint in optimal control such that any exploration of a better trajectory always ends in the safe set. Our main contribution in this work is to build a residual learning strategy to learn a local approximation of the overall robot dynamics iteratively. Our contribution is threefold. First, we derive the residual learning strategy for learning local robot dynamics in the MPC problem. Second, we show this method exhibits improved robustness against parameter tuning and data scarcity compared to vanilla dynamics learning using simple regression. Third, we demonstrate the deployment of this learning system on scaled and full-size race car. In dynamics era learning, we first assume the existence of some unknown nonlinear modeling error E of xk and uk on top of the nominal model's prediction f of xk and uk. We then derive a regressive learning strategy to learn local approximation of the function E. How we obtain the dynamics of the robot can be divided into two parts. In prior driven parts, we take a conventional differential dynamic programming or DDP-based approach and take the first-order approximation of the affine time-varying dynamics model, which produces the A, B, and C superscript F matrices in the final dynamics function. Then, in the data-driven part, we query the sampled safe set for sequences of state and action pairs that are in the neighbor of the robot's current state. We then obtain the difference between the nominal model's prediction of the next step and the ground truth in the dataset. This generates a signal for the modeling error. We then perform a weighted regression to individually regress the errors in ATV matrices, obtaining the final learned dynamics function for learning MPC. We now present the results of the simulation experiments. The graph shows the robot making progress towards the minimum lap time by simultaneously learning dynamics and optimal control policy. The blue and red graph compares vanilla full regression, which does not use the dynamics model as prior, and our error learning method. For each setup, we swept control rate cost, or CRC, across two orders of magnitudes. CRC governs the learning rate of learning MPC, and any real-world learning algorithm should be robust against its tuning, since the optimal tuning cannot be guaranteed when transferring to the real world. Our method exhibits greater robustness and succeeds even when CRC tuning differs greatly. We then move on to real-world scaled hardware experiments on 1/10 scale hardwares. We run both full regression and our error regression for 10 trials and measure the success rate. We observe that in the example trial comparison, our error dynamics regression is able to converge to a consistent lap time over 20 iterations, while full dynamics regression often fails halfway. Next, we visualize the learning progress of the error learning MPC. The figure shows the first, 5th, and 20th iteration, which shows a progressively increase in speed and convergence to an optimal race line. Finally, we demo a full-scale experiment on a race car in the Indy Autonomous Challenge. We run the learning MPC policy and recorded 20-lap performance. The zoomed-in plot of the hairpin turn shows the trajectory of the 1st, 5th, and 20th lap, suggesting convergence to optimal cornering. The video demonstrates experiment progress. First, we run a tracking MPC on the center line at low speed to obtain the initial sample safe set. Then, we let learning MPC take over and iteratively learn both the model and the policy. Here we show the performance of the cornering at the chicane after 5 and 10 iterations. In conclusion, we present learning MPC with aerodynamics regression, which leverages simple machine learning technique to learn robot dynamics and go from little understanding of the dynamics to the mastering of its handling limit. We show that just learning the local dynamics functions landscape is sufficient without building a convoluted expression for the robot's dynamics in all operating points. We also emphasize that the learning is reference-free, as no notion of optimal trajectory was ever given to the robot at any point, and nor was it given optimal control references. On the downside, the method is limited by the expressiveness of local linear approximation, which may fail if the neighboring states are too far away in the learning. Also, the whole learning MPC paradigm exploits the iterative nature of the task and needs to be reformulated in non-iterative cases. And that is all. Thank you for listening.